this is Viz 2320 Computing 2, and this is the first video in the sequence on numerical Python looking at the Numpy module. Okay, so first of all, why do we need Numpy? So often in physics we're dealing with data which is a collection of numbers, a sequence of numbers. So that might be a sequence representing a particular measurement, or it might be x, y points on a graph, or it might even be data points in an image. So Python has a perfectly good list data type that provides us with an ordered collection of items. So that's where you can index each of the items with a number. So the list lets you index into it, and you can pull out each item by its position in the list. And it's a good general purpose data type. It can store any kind of items you want in the list. It can be any mixture of data types. But that's also its weakness, because it means that it's not very memory efficient. So items in the list can be stored anywhere in the computer's memory at all, and certainly not necessarily close together in a nice contiguous block. And as a result of that, it's not very fast to carry out calculations or operations on each element of the list in turn. There's another problem, and that is that in physics we're often dealing with data in the form of two-dimensional tables, or maybe even 3 dimensions. So you have some quantity that you are measuring as a function of more than one parameter at a time, and so you end up with data that's naturally 2 or 3 dimensional or even higher dimensions. And the Python list is really only a 1-dimensional thing. It's just a simple sequence of items. You can sort of fake a 2D data structure, 2D table of numbers, by making a list where each element is itself a list of items. But it's pretty clunky, and it's hard work to work with it. So this is where Numpy comes in. So in contrast, Numpy, like a list, is an ordered collection. So you still use indexing with numbers to get at the elements in it. But unlike a list, each item in the array must be the same data type. So that has an advantage. It means that you can store everything in a nice single block of memory, because you know that everything is exactly the same size. And that also means that it's fast to go and do math functions, because you can work with the whole array at one go. And in fact, Numpy includes lots of math functions that are designed to take advantage of the fact that modern computer processors can work in a sort of vector mode and can work with a whole list of numbers all in one go in parallel. And it's also very easy in Numpy arrays to have multiple dimensions. They're sort of built into the Numpy array. So in this video we're going to have a quick revision of Numpy and Numpy arrays from Computing 1. We'll be looking at creating arrays, we'll be looking at indexing arrays, and looking at using some of the Numpy math functions. Okay, so let's go over to our spider then. So the first thing we need to go and do is import Numpy. So by convention, Numpy is normally imported as np. So all the Numpy functions will then be available as np.something. We're going to start off by simply creating an array from a list. So let's call our variable a. That's going to be np.array, and then we're going to make use of this function. So we have open round brackets, and now we're just going to give it a list to make the array out of. So there we go. That's the numbers 1 to 9. So in square brackets, that's a Python list, and I'm feeding it to the array function, and it's going to turn it into a Numpy array. And if we look in the variable explorer, then we see we've created this variable a. It's got type int64, it tells us, and it's got a size of 9 long, and it says there it's an array. And if we double click on it, you can then have a look at it, and you see we've got 9 rows indexed 0 to 8, each containing the numbers 1 to 9. Okay, and if I ask it what type A is, it says it's a Numpy ND array. I could ask how long it is. It tells me it's 9 elements long. That's not a great surprise. I can also ask what shape it is. Whoops. Shape is an attribute, not a function. No brackets needed there. So there we go. It's 9 by nothing, meaning it's a 1D array. It's got just a shape of 9. Okay, I can also create a matrix, so a 2D array, so that's very similar. Create np.array, and now I'm going to create, rather than a list, I'm going to create a list of lists. So we're going to have 1, 2, 3. So what I've created here is a list which has 2 elements in it. Each of those elements then is a list of 3 numbers. And the first thing to say, if you're creating a 2D array like this, you need to make sure that each of your sublists has the same number of elements, because as we see, we're going to create a 2D array where each of these is going to represent 1 row. So there we go. If I pull up in the Variable Explorer, you see again it's integers. It's now telling me it's 2 by 3 in size, and if I open it up, you'll see that's 2 rows by 3 columns. And clearly, if my 2 sublists when I created it didn't have equal sizes, it'd be trying to create 1 row with a different number of columns from the other row, and that doesn't really work as a table, so it wouldn't accept it as a valid input. Okay. Now, if I want to actually go in and extract variables out of this, well, first of all, let's just ask how long is m. So it tells us it's 2. So if you ask how long a Numpy array is, it tells you how long the first dimension. So 9 for the case of A and 2 for the case of m. If we ask it what the shape of m is, then it tells us it's 2, 3, meaning it's 2 rows and 3 columns. So Numpy always works rows first. It goes rows, columns when you have a 2D array. Okay, if we actually want to know how many elements there are, well, we could just multiply the elements of its the elements of its size. So with its shape, we could say it's 2 times 3, or else you can use the size attribute, which tells you that m has 6 elements and A has 9 elements. We can also ask how many dimensions it has. Again, you could just count the length of the shape. So the length of A.shape was just 1 long, so it's got 1 dimension. The length of M.shape was 2 long. Or I can use endims, so I can say A endims, whoops, endim, even, and M endim tells us it's 2. So endim tells you the number of dimensions of your Numpy array. So that's kind of the basic properties of it. The other thing we might want to say is, well, what actual type is each element? So in these 2 arrays we've created, they're both integers. So int64 means it's an integer which is using 8 bytes of information per number, and that sets what the biggest size of integer we can store in the array is. So Python itself will work with integers up to an infinite size, but for Numpy it needs to know how big each element is, because it's going to use that to access the memory to store each element in efficiently. So it has a certain number of fixed sizes. So int 8, 16, 32 and 64 are the common ones, meaning a 8-bit or 1-byte integer, so that can store -127 to -127, or int 16 does plus or minus 32,768, and int 64 will go and give you a much bigger number, which I don't know off the top of my head. Okay, we can also find out what the data type is by asking it with the d type. So a.dtype tells us it's int64, m.dtype should be the same. Whoops. It does help if you actually type the right letter there. There we go, int64. Right. Okay. So dtype is telling us the data, the type of the data we're storing there. Of course, if you have an integer array and you want to turn it into a float, then you can use as type and tell it what float you want to go to, what data type you want to go to. So I can tell that into a float, and now it's going to return something which has, you see, it's got decimal points after each number. If I actually turn it, create say M2, so now I've got another array here, M2, and you see that's float 64. So it's simply just converted the numbers from, instead of being an integer, doing floating point numbers. Okay, how can I actually get in at the individual elements themselves? Well, the simplest thing is just like a list. You do A, and if I do 0, then that's the first element, and 1 is the second element, and so on, up to A8. And if I ask it for something beyond the length of the array, then it stops and tells me it's got an index error. And just like a list, I can index with negative numbers, and it works from the back. So that's the last element, that's the second last element, and so on. I can also, as well as indexing just with a simple element, simple number, I can give it a list of numbers to index. So now what I'm doing, I've got the square brackets, meaning I'm going to index A, and then in the thing I'm giving it, rather than giving a number, I'm giving it a list of elements. And that returns an array, which is a list of which is the ones I was after, the first element, the third element, and so on, up to the last element. I can also use the slicing notation that you've seen before, so I do from the first value to one after the last value, and I can specify a step, so it's start, end, and step, and it goes from the start to one less than the end in steps of in the step size you give it. And there we go, so that's pulled out the even numbers. Or alternatively, if I didn't want to go and specify a start and stop, I can specify 2 colons, meaning from the start to the stop in steps of 2, and that you see is in fact the same as I had before, so 0, 2, 4, 6, 8. Or alternatively, I could give it a start and not a stop and a step, and that'll do from the start to the end in steps of 2, and that's the same as I had before. Or if I want the whole thing, I can give it just 1 colon, which you can read as from start to the end in steps of 1, which is the whole array in this case. So you can do quite a number of flexible things with indexing like that. If you have a 2D array, then the indexing is done by giving it 2 numbers separated by commas. So 0, 0 is the first element, 0, 1 is the first row, the second column, and the first row in the third column, and then you can do first row, second row, second column, and so on. And you can do the same rules about using the slicing operations with the colons. So I can do M colon comma 1, which means all the rows, second column, and that pulls out that middle column there. Okay, we can demonstrate exactly how this indexing is working as well by doing the other way around. So far we've just been reading the array, but you can also go and set values in the array. So to demonstrate that, I'm going to create a new array which is going to be full of zeros. I'm going to make use of the np zeros function to do that. So I'm going to call it Z. I'm going to do np zeros, and now I have to give it the shape of the new array of zeros I want. So I'll give it a 2D array which is 10 columns by 10 rows. Actually no, let's make it 10 rows, 5 columns. And by default it'll give me a float, but you see there's a d-type parameter there that I can set to tell it to do something other than a float. Okay, so there's our Z. So I open that up, you see it's a nice 5 columns, 10 rows. So in order to go and see what we're going to do to this, I'm going to change some of these zeros to ones. So first of all, let's start with Z 0, 0. equals 1. So now you see all of those are zeros, and I've set that value there in the corner to be 1. Okay, if we reset that back to all the zeros again, and now I'm going to change, and I'm going to make let's have the third column. So I specify a colon for the first index, that's the row. So I'm saying all the rows, and then remember we start indexing at 0, so 0, 1, 2, this is the third column, equals 1. And there you see, we've set the third column equal to 1. And now I could say change it so that the let's have the third row and all the columns, whoops, equal to 1. And I need this to refresh, so I'll have to, whoops. Okay, so after I managed to have Spider fall over with the Variable Explorer, I've restarted and I've recreated my Z array. So there it is. So this time I'll remember to close the window before I start changing it. So now what we're going to do is we're going to change the third row down to be all ones. So the third row down has a row index of 2 because we start at 0. And I want all the columns. So I put a colon there, equals 1. And there you see, third row down, I've pulled out all of those ones there. And you can get more complicated, so if I reset it all back to zeros again, so I can now do, for example, every second row and every third column. Actually, let's do it the other way around. Let's have every third column starting from the second one and every second row equal to 1. And there you go. Every third row starting from the second column down and every other from the second row down, every other column I've set to 1. And that's all just with that one line. So the two numbers give us the row and then the column, and you can use the slicing operations, in this case say starting at 1, going on to the end, every third row, and starting at the start, going to the end, and every second column should be equal to 1. And so it gives me exactly those points there. So you can very quickly and easily get out the bit of the array you want to work with. You can change it, you can do what you like with it. So of course creating arrays that are either created from a constant or created all zeros, or indeed I could also have one that's created all ones. So there's a ones function Numpy that's exactly the same as zeros, so I can specify the shape I want it to be, and as you'd expect, it just gives you all zero or all ones everywhere. That's all very well. Of course, it's not particularly helpful. So first of all, we've got other ways of creating it. We can do the same thing as we did with range. There's a range function in Numpy. So a range, and that takes a start, a stop, and a step, just like the ordinary range does. But unlike the ordinary range, these start and stop and step can be floating point numbers. They don't have to be integers. So I can create a simple one. Well, if I just do a range 100, for example, then you see it's just simply created an array going out, counting up to 100. Well, from 0 to 99. But I can also do, for example, 100 to 1. And in that case it's going to count Oh no, it's not going to do that because it can't count from 100 to 1 in steps. So to positive steps, and by default it'll have a step of 1. But if I tell it to have a step of -1, then it'll count backwards from 100. In this case, down to 2. Remember, it's always going to end up. Well, it's always going to end up stopping one short of where you specified the last one to be, just in the same way that range does. And equally easily, I could create one that was counting from 1 to 100 in steps of 3, or whatever else I wanted it to do in, and it does what you'd expect. So that's one option. Let's say you can also have floating point numbers there. The other way that's quite useful is the Linspace function. So np.linspace. This gives you a linear spacing from again a start and a stop value, but now you specify a number of data points, and you can also specify whether it should create with a including the endpoint. So this is actually for, say, creating a value of for creating a scale for a graph or something. This is in some ways much easier. So you might want to create from, say, np.pi to np.pi. So Numpy has the value of pi as a constant handily built in for you, and you might want to do that in, say, 360 steps. And now you see it's created a floating point array, which does indeed go from pi minus pi to pi. Okay, so that's your basic ways of creating arrays. There's also, I should say, a Logspace. So let's have. So Logspace, you see here again, it's got a start, a stop, and a number. But now what it creates you from is numbers from the by default 10 to the power start to 10 to the power stop in a logarithmic spacing. So if I create one from, say, -3 to 3 in 7 steps and show you here, then you start at 0.01, it just goes up in orders of 10. Multiples of 10. So again, if you're depending on what you're trying to plot, that could be very handy if you want to plot or want to work with numbers which go over some sort of logarithmic scale. Okay, so let's have a look at what else we've got in NP. So the easiest way is just do np dot, hit tab, and here you see a whole long list of numbers, of functions rather, including some trig functions. So in fact, Numpy includes every type of function you've got in the math module. Unlike the math module, however, it works with an array. So just to show you how these are different. So if, for example, let's import math as well. So if I created a list, I'll call it XL. So let's have 0.1, 0.2, 0.3, 0.4. So this is a Python list. So if I say type XL, it's going to tell me it's a list. So now if I do math.sign XL, it's going to tell me it needs a floating point number. So in order to go and do that calculation, in order to calculate the sign of all those numbers, what I have to go and do is something like this. So I'd have to put an explicit for loop round, and then it would do it, and you'd see YL as a list, which is where it's calculated. That's okay, but it's actually very, very slow because you have to go and manually iterate over this list, and you see it's also involving quite a lot of typing. The Numpy equivalent, well, we've got our x2, which is 100 elements long, and I simply just do np.sign x2, and there we go. It's calculated the sign of all the numbers in one go without having to stop. What's also good about this is that some of its maths functions are a little bit more sensible. So you remember from the previous videos, if you try calculating the square root of minus number with the math module, it goes and gives you weird results, whereas np.sqrt x2 quite happily just goes off and does it. And you can say, well, hang on a second here, x2, sorry, let's even do it with x then, rather than x2. Okay, so it's not complained at me, it's simply gone and calculated that some of these things are imaginary and it can't work out what the square root should be without using complex numbers. Okay, the other thing is that ordinary maths operations work kind of as you might expect with Numpy arrays. So again, I've got this x array, which is nice and long there. So if I just want to multiply it by 2, I can do 2 times x, and it just simply multiplies every element by 2. I can do x over 2, it does what you'd expect. Now this is where this is a little bit different from a list. So with XL is my list. If I do XL plus XL, then with a Python list, that simply just duplicates the list. So it simply just adds, if you do plus on two lists, it simply adds the element one list onto the end of the other elements. It does the same as an extend or a concatenate. With the Numpy array, if I do x plus x, what it does is add element 1 of the first list to element 1 of the second list, and element 2 of the first list to element 2 of the second list, and so on. So it is doing something that's slightly different there from what you're doing with a list. So that's one to watch out for. Okay, and then there's all the other functions you can choose to play with. So as I say, if you do np dot, then you'll find that there's just a huge number of the functions already built in for you. In fact, probably slightly more than you have in the math module. So my firm recommendation at this point is to give up using the math module and just use the Numpy module for all of your code, because it means if you are working with an array, things will just work with an array and you don't have to think about it. And if you're working with ordinary numbers, and if I just do np sign 0.1, then it just does it as well anyway. So it's as good as the math module, and in many ways it's better than the math module. Okay, so things I've shown you in this video then, I've shown you how you can create arrays either from a constant or from a using the ones or the zeros functions, or the a range, or the linspace, or the logspace. Of course, quite often what you want to go and do is load it in from a text file, and so there's a np.gen from txt function, and we'll look at that in the third video in the working with files. So have a look at the third video in the working with files section for more about gen from txt. I've also gone through indexing. So indexing works more or less like lists, except that if you have a 2D array, you can index it with 2 numbers. If you have a 3D array, of course, you index it with 3 numbers. You can index things by giving the list of numbers to pull from, in which case it doesn't give you just one element out, it gives you a list of elements out. You can use the slicing operations, that's with the colons. So a colon on its own means everything. You can specify start value colon stop value, or you can do start value colon stop value colon step, or if you don't specify the start and stop values, it assumes you means the very start of the list and the very end of the list. So you can do things like colon colon 2 to mean every other element in your list. And you can use those slicing operations for either specifying the row or the column of a 2D array. You can set individual elements of the array by just simply indexing into the array and setting the value that way. And you can even, as it turns out, set whole rows at a time like that. And then I've shown you the that the Numpy maths functions know all about arrays, and they know to go and work on each element in the array, and also that when you do the standard operators, so plus, times, divide, and so on, that they also work as you might expect on an array and do whatever it is for each element in turn. And that means if you have a whole vector or a whole list of values you want to go and do the same sum on, so like a whole sequence of measurement values, then you can write it just as you write it for doing one value, but you're actually operating on all the values at the same time. Okay, so there we go. I think that's then covered everything that I said we'd go and cover in this video.